Hi, here we'll go through the topic or the section first law of thermodynamics. First of all, we'll go through the list of subtopics, then we'll go through the remaining things. In this section, we are having first law of thermodynamics applied to a process, first law of thermodynamics applied to a cycle, the concept of energy, internal energy, enthalpy, how internal energy differs from enthalpy, better understandings of properties and path functions. Then we are having perpetual motion of kind 1, specific enthalpy, specific internal energy, relations between Cp, Cv, R and gamma. Cp is nothing but specific heat at constant pressure, Cv is nothing but specific heat at constant volume. Flow work, steady flow energy equation or SFEE, application of SFEE on nozzles, turbine, compressors. Then we are having throttling process and free expansion. And in the throttling process itself, we will see the difference between throttling process undergoing by ideal gas and a non-ideal gas, and same for free expansion. Then we will go through unsteady flow process or transient flow process. From this topic, we can expect 7 to 9 marks. Note that from this small topic, we are getting a marks of 7 to 9 marks. It's just kind of a lottery, and believe me, it's one of the easiest topic you can ever get in GATE itself. So if you are spending fairly good time, you can score all the 9 marks or all the 7 marks coming from this section. So now we will go through the portions in detail, or just we will see the overview of this portion. First of all, let's see the first law of thermodynamics. First law of thermodynamics is nothing but conservation of energy principle applied in thermodynamics. What is conservation of energy principle? Conservation of energy principle is where we say that energy cannot be created nor be destroyed, but can be converted from one form to another. So this happens during a process, right? So we will apply this in a thermodynamic term. We know that for a system, it will be having a total energy or total stored energy, right? When it undergoes, there may be heat transfer or work transfer, there will be change in total energy. So in a process, we are having three energy terms, that is change in total energy, heat transfer and work transfer. So if we balance these three terms, we'll get the first law of thermodynamics applied to a process. A cycle is nothing but a combination of various processes such a way that initial and final final point are same, right? So if we apply these first law of thermodynamics to process, in all the process, finally we will be getting that sum of heat transfer is equal to sum of work transfer. That is, algebraic sum of heat transfer involved in this all the process is equal to algebraic sum of work transfer in this all the process. Then you may think, what happened to the internal energy? Internal energy is a property, right? In a cycle, change in property is nothing but zero itself. You will come to know about these things when we go into the deep. And here I am just giving you the introduction and just making you to familiar with these terms. Okay. Now, for ideal gas, we are having few relations like U is equal to, or internal energy, total internal energy is equal to mCVT. Similarly, we are having total enthalpy is equal to mCPT. Remember, this is only for ideal gas. Similarly, change in specific enthalpy, we can write it as CPdt. If it is change in enthalpy, it will be mCPdt. Similarly, change in specific internal energy, it will be CVdt. Again, we are having two relations, that is Cp minus Cv is equal to R. R is nothing but characteristic gas constant. Here we are having one more relation, that is Cp by Cv, which is equal to gamma. Gamma is nothing but adiabatic gas index. And we will have to know the values of Cp, Cv, R and gamma for air, which is very commonly used gas in almost all the questions. In many questions, they will not be giving the values, so we should be knowing these values, and will be very much helpful while we are doing problems also. Sometimes they may be given in the question, but given us general data in the question, but if you already know the values, why should we refer there, right? So we can save some time also. Next, we'll go through steady flow and unsteady flow. Let's see the difference between steady flow and unsteady flow. A steady flow process is nothing but in a flow process where properties are not changing with respect to time. If the properties are changing with respect to time, then we will call that process as unsteady flow process. For steady flow process, we will derive an equation that is called steady flow energy equation, or commonly known as SFEE. And similarly, for unsteady flow process, we will be having energy equation as well as mass balance equation. If we know these two equations, generally people consider unsteady flow process or as bit complicated, and many of them leaves that. But I promise you that if you know these two equations, you can solve any problems from unsteady flow process. Here I am having a previous year gate question. Listen to it. A rigid insulated tank is initially evacuated. The tank is connected with a supply line through which air, in bracket assumed to be ideal gas with constant specific heats, close the bracket, passes at 1 MPa, 350 degrees Celsius. That means we are having a valve, or we are having a pipeline through which air is going through. This and the next part of question, a valve connected with the supply pipeline is opened and the tank is charged with the air until final pressure inside the tank reaches 1 MPa. The final temperature inside the tank is, that is the question. Various options are given, like greater than 350, less than 350 degrees Celsius, equal to 350 degrees Celsius, and D may be greater than, may be less than or equal to 350 degrees Celsius, depending on the volume of the tank. Here I will explain the question once again. Here we are having a supply pipeline through which air at particular temperature and pressure is flowing, that is 350 degrees Celsius and 1 MPa, right? And this is connected to a tank using a valve. We are opening the valve and the tank is previously evacuated. Before opening the valve, the tank was previously evacuated. So the moment we open the valve, what will happen? The air which is flowing through the pipeline will rushes to the tank, right? When the pressure inside both the tank and pipeline becomes equal, that is 1 MPa, the flow process will stop. The question asks that what will be the final temperature inside the tank. Here you can see that the tank we can consider as our control volume. Okay, inside the control volume, we know that as time passes, the property called mass increases, right? Initially, the mass inside the control volume was 0, but as time passes, the property mass called mass is keep on increasing. So it is a clear case of unsteady flow process. So in an unsteady flow process, I already told you that we are having two equations. One is energy balance equation, one is mass balance equation. If you apply that, you can simply get the answer for this question. Sometimes they will be specifically asking what will be the final temperature inside the tank, so like something like that. Even that is also easy question only, you can easily find that. So what I am saying is that be careful while you are learning unsteady flow process. Believe me, it is easy. Then we are having throttling process and pre-expansion process. In a throttling process, let's see what is a throttling process. Consider that we are having a pipe through which a fluid is flowing at high pressure and there is a leakage at some part of pipe. What will happen? That particular fluid will leak through that pipe, right? When the fluid comes out through that pipe, there will be a large pressure drop. That means final pressure of the fluid will be very much less than the pressure which initially it was having. Then we can call that process as throttling, and that hole as the hole through which the fluid came out as throttling valve. So what is the throttling process? The simple process in which if the associated pressure drop is huge, when the fluid passes through narrow path, we call that process as throttling. And we'll see how we are arriving. We'll be finding some relations for this, and we will see what is the difference between throttling process undergone by an ideal gas and non-ideal gas. And regularly questions used to come from this part. and it's easy. Once you understand this thing, it's very easy. From the class itself we can understand. Once you understood, you can solve any questions. It involves very least calculation. Then we are having free expansion. Let's see what is a free expansion. Consider we are having a compartment, a cuboidal compartment divided into two. One part is vacuum and in one part we are having some gas at particular pressure and temperature. Let that partition is be some membrane kind of thing. By making some disturbance we can break that. That means we can break that according to our will. Once we break that, what will happen? The gas inside the compartment will rush to the vacuum, right? This sort of process we call it as free expansion. Once again, here also there is some difference between free expansion process undergone by ideal gas and non-ideal gas. Questions used to come from this part regularly, and this part also very easy. Sometimes it used to be conceptual question, sometimes it used to be problematic question. If you are getting this question, consider that you are lucky. And that's all about first law of thermodynamics. And I already told you we are getting 7 to 9 marks question from this portion. So let's roll on this topic, right? Let's see the questions, the type of questions we are getting from this portion. The one marker question used to be usually very straightforward and easy questions. If you know the concept which you already told you, I mean the list of concepts like throttling, a free expansion, unsteady flow process and all, how it is applicable to ideal gas and all, definitely you will be able to score all the one marker question without much difficulty. Okay, here I'll tell you one question. In a reversible process, constant non-flow process, constant pressure non-flow process, heat input is given by. In a reversible constant pressure non-flow process, heat input is given by. Option A is change in internal energy, option B is change in enthalpy, option C is change in entropy, option D is work output. We know that for a process, first law of thermodynamics will be dq is equal to du plus dw. That means heat transfer is equal to sum of change in internal energy plus and work transfer. Here we are saying that constant pressure process, for a constant pressure process work transfer will be 0, so the heat transfer will be equal to change in internal energy. So it's pretty straightforward question, right? This sort of question you can expect for one marker and you can easily score that. And the question will be related to throttling. I already told you many times about how there is a difference between throttling process undergone by ideal gas process and non-ideal gas process. There used to be question from that part also. Here I don't want to break the suspense, so you'll learn when you go through that. Okay, there is a slight difference. And what is the work done or heat transfer in a cycle from a PV diagram? That means there will be PV diagram given. From that we will have to find the work transfer or heat transfer. One question I have seen that they are given a PV diagram with a circle as a region, and they are given the diameter of that circle also. We are told to find the efficiency of that cycle. Efficiency is nothing but heat output, work transfer, and positive work divided by sum of heat transfer. How much heat we have given, right? So anyway, here also I am not going to explain that. That's also a pretty straightforward question. You can find it easily. Then here I would like to share one question. It's very interesting question. I'll read the question. A person starts 60 watt table fan in an insulated room of volume 86.4 meter cube. The person expects to cool the room from 32 degrees Celsius and allows the fan to rotate for 4 hours. If the specific heat at constant volume and I mean Cp and Cv values are given and R value is also given. After 4 hours, what will be the final temperature of the room? The question says that we are having a room in which a person starts a fan and operating it for 4 hours, and while those 4 hours he is outside. Okay, when he comes back, he expects the rooms to cooler than initial temperature, that is 32 degrees Celsius. Here we are supposed to find the final temperature. What do you feel? Whether the temperature will be lower than 32 degrees Celsius or higher than 32 degrees Celsius or same? Okay, anyway, I'm not going to give you the answer straight away, but I'll give you the clue. I hope many of you already know the answer, right? Still, let's discuss on this. We can consider this room as insulator room. Okay, it is already given in the question. So in an insulator room, heat transfer will be 0, right? So a process is happening here. We can apply first law of thermodynamics to a process. So we are having dq is equal to du plus dw. Here dq is already 0 and we are having du plus dw. Here fan is rotating for 4 hours, right? That means we have to consider that as a work transfer. You will understand why we are considering rotation of fan as work transfer when you go through it. So we are having du plus that work transfer. We will be getting particular quantity of work is equal to du, because here we are giving the work to the system, that is we are considering as negative. Yes, here I like to tell you that we will have to be very much careful when you are applying the side convention for heat transfer and work transfer. Work done on the system is taken as negative, work done by the system is taken as positive. Heat transfer to the system is taken as positive, heat transfer from the system is taken as negative. You should remember this always. It is very important. If you are making even a slight mistake in this case, will end up in big mistake.